What up, everybody? Thank you so much for being here. Appreciate you guys taking time to join us, especially on the cusp of a long weekend. True nerds. I love it, man. So, again, thank you, Lori, for your talk about Llama Index. A little bit of self-promo. I got a course on LinkedIn Learning all about Llama Index. So if you guys have access to LinkedIn Learning at all, check that course out. It's like 7 hours. You can finish it this weekend. You guys, you guys seem like the type of people that might want to do that. So definitely check that out. So I don't have slides or anything. I'm not going to do slides, but I will have code and pictures. And we'll talk about embeddings as well. I think it's a good bridge between text-only kind of embeddings that Lori was talking about, and then what Jay Rogerson talked about with multimodal RAG. What are embeddings? Give me some answers, some thoughts. Like when I say embeddings, what do you guys think of? Really big arrays, yes. Massive arrays. What else? Representation of data, yes, right? Taking really complex data and finding some way to represent it. Are all embeddings equal? No, right? Like different embedding models, different modalities will give you different embeddings. So that's what I hope to kind of communicate in this talk, is just to show you different types of embeddings, but then also different things that we could do with them beyond just text search for RAG. So let's go ahead and get on with it. I will be using the open source library, FiftyOne. I don't know if you guys have heard of FiftyOne, but it is cool. Just pip install FiftyOne, and you can use it, and you can do everything I'm doing here. But really, it's just the medium of communication. So I'll quickly go over the code. If you guys got questions about the code, you're more than welcome to ask me, and I'm happy to answer questions. But let's go ahead and get on with it. So first thing I'm doing here, I'm just downloading some data. In this case, this is a small segment of the Stanford CARS data set, right? Putting it into a FiftyOne data set object. Don't worry about it if you don't know what that is. Dropping some fields that I don't need. And now this is kind of the interesting stuff that I'm doing. I'm downloading 3 models for embedding from the FiftyOne Model Zoo. I've got a clip model. Have you guys heard of clip? Or anybody? Do you guys know what clip does?
It's a 2-tower embedding model. It has an image tower, a text tower, and tries to locate where images are.
Yeah, so clip, contrastive language image pre-training. We have a image encoder and we have a text encoder, right? And the image encoder, I think the clip paper, they used a VIT huge, something like that, and then some type of GPT model. And there's a projection matrix, so you kind of take these embeddings from text and embeddings from images, project them into the same space, and what you could do is some interesting stuff that we'll see in a little bit. But essentially what we're trying to do is we're trying to make embeddings from the text model, if they correspond to embeddings from the image model, like we're trying to, during training, push those embeddings closer together if they actually correspond, or pull them apart. So this is done through a contrastive loss function. And then I'm also taking, I took small models here just because I ran all this locally, but I've got MobileNet and DenseNet. And we are going to look at the embeddings that we get from these models. FiftyOne, when you do pip install FiftyOne, I'm going to say that at least 51 times during this presentation, you get access to this awesome tool called FiftyOne Brain, and it just allows you to do some really interesting things. One of them, we'll get to a few of them actually in this notebook, but to compute embeddings is just a simple one-line call. We just take our dataset object, .compute embeddings, what model do we want, and where in the dataset object we want to store those embeddings. So I'm computing embeddings here for clip, MobileNet, and DenseNet. And then, they're really large arrays. Really large arrays are really hard to visualize, right? If I ask you to try to visualize a 2048 dimensional space, I don't think any of us could do it. But what I'm doing here is I'm going to project it into a lower dimension using UMAP. Are you guys familiar with UMAP? Uniform manifold approximation, I believe is what it is. But essentially taking this really large array and projecting it down into 2 dimensions so that we can kind of visualize this as if it were on a scatter plot. I'm doing that for each one of the embeddings that we have: Clip, DenseNet, and MobileNet. And this is going to be interesting when we open up the app and look at the embeddings panel, because now we can see how the different models are representing the image that we're going to look at. So part of FiftyOne Brain is you could also compute uniqueness, and we'll see all this in action. I'll gloss over this, and I'll share a, if you guys are interested, I'll share the link to the GitHub, and you can download the code and try it yourself. But essentially, we can give, with embeddings, we can give each image in our data set a measure of uniqueness, which is pretty cool. And we'll see what that looks like in just a second. What I'm also going to do is create a similarity index. That way we can search over these embeddings to find similar images. And then also a similarity index to do kind of, in a sense, cross-modal type of search, going from text to images. If this is too much code for you guys, raise your hand, let me know. I'll try to breeze through it as quickly as possible and just get to the good stuff. Another thing we could do is compute representativeness. And so representativeness will give us some sense of the most common types of images in our data set, or the least common types of images in our data sets. So this is all really, really useful if you're working with visual AI data. So without further ado, let's just go ahead and jump right into it. So I'm going to launch the FiftyOne app here in the notebook. Okay, so this is the Stanford Cars data set, all right? So the first thing I want to do is I want to open up the embeddings panel. And what we want to do here, I'm going to just close this. And what I'm going to do here is I'm going to select one of the embeddings first. Let's select the clip embeddings. And now we kind of see, we're visualizing embeddings, essentially. And what this allows us to do here is, like, we can zone in here and say, okay, this looks interesting. There's like a cluster of images right here. What are these? And we highlight them, and we can see, oh, that's cool. They're all like just these atrocious Hummers. You know, like, honestly, I can get lost looking at these. If Jimmy knew how much time I spent just looking at embeddings, he'd be unhappy. Now you know. But this is cool because, you know, it gives you a way to kind of see what is in your data set, right? Like, this is just a small data set of something like 2,000 images, but imagine if you had millions and millions of images. It's very hard to get a sense of what is in your data set, and so embeddings allow you to do that. What else is, well, what I find also pretty cool about this is, you know, right now we're looking at clip embeddings, right? But we can highlight any given picture, right? I can highlight this picture, and now I can see how the model is representing this image. You'll notice that the space, this embedding space, changes when I change the model. So if I go to DenseNet, you see that embedding space changes dramatically. It's kind of more spread out. If we go to MobileNet, you can see that that embedding space is, it changes. Okay, that's cool. What else can I do with that? Well, I could take this, right, and I can find images that are similar to it. So in this case, what I'll do is I'll find maybe the 5 most similar images to the one I just highlighted, right? And let's see those similar samples, right? And we can, you know, select them all, and right, we could select them all. We could see where they lie. So remember, we're taking like a high-dimensional space and compressing it into 2 dimensions. If we had a 3rd dimension here, in that 3rd dimension, these might kind of be a little bit more similar, a little bit more close. Sorry?
Use the compare for a different model.
Yeah, so we could do that now. We could check it out, right? So right now I'm looking at, in this case, I used clip, right? So right now, if we change it to the clip embedding space, yes, they're all similar, yeah, right? But I can now change it. I can look at DenseNet, and we can see DenseNet, these aren't as similar, right? We could see here in MobileNet, as we're just looking at, they're not as similar, right? So we can also change that here, right? Going back to our original image, sort by similarity, and then let's look at the DenseNet 5 most similar. Oh, did not do that right. Where did that go? Oh, all right. Let's go to DenseNet. 5 most similar images, right? Of course, if we highlight all those, and you can go through that same exercise and kind of see how these different models represent these particular images. So yeah, that's one cool thing that embeddings allow us to do. Another cool thing that embeddings allow us to do is we could do some type of cross-modal search, right? So let's go ahead and do that. Let's do some text similarity here. So in this case, the other 2 models, they're image-only models, so I can only use clip to do a text similarity search. But I could do something like really ugly gas guzzler. How do you spell guzzler? Guzzler, right? Okay, it's quite accurate, right? If anything, they are really ugly. But this is cool. It allows us to do some interesting things like that. Another cool thing we could do with embeddings, we can actually do kind of a reverse image search. So I have this image data set, right? We've got this massive image data set, and now we can take images that are not part of this image data set and try to find things that are similar in our data set to this foreign image, if you were. So let's pull this up. We'll do a reverse image search panel here. I'll just use I'll use MobileNet. Why not? No, let's stick with clip. Let's do 5. Let's upload a file, and the file I will upload is it's a picture of my son on a tractor. He loves tractors. He's also cute. And then we could do a search for that. I don't reckon there will be many tractors in this data set, but we can see what clip thinks is most similar to this particular image. Right. And you can see we're picking up, like, you know, bigger cars with some type of color similarity to that. So it's cool. Like, embeddings are awesome. They allow you to do some really interesting things. Now, as promised, let's look at some other things that I'd mentioned. One of them being uniqueness, and you can see here that we computed uniqueness, you know, using clip, MobileNet, DesNet. I only computed representativeness using clip, but we can kind of do a sliding scale here, and we can say, okay, what are the most unique images in our data set, right? And you know, this is quite unique, right? Just a shoe in front of it, and we could do the opposite. We could see what are the most kind of non-unique images in our data set, and we could see that right there. Yeah.
How is uniqueness computed based off like distribution, like common like backgrounds, like
Yeah. So under the hood, I outlined it here. I'll send you guys a GitHub repo. I think Jimmy, we'll email you out all that stuff here. But essentially, I kind of outlined the algorithm that we use here. And essentially, we're using embeddings. Then we do a k-nearest neighbor search. Then some distance-based scoring, and then you know, you can mess around with that a little bit. The thing is, the FiftyOne brain, as of now, is that part's not open sourced yet. It might be soon. But once it's soon, you will have all the details, gory details about how uniqueness is computed. But for right now, this is kind of the algorithm, and the rest of it is a little bit of secret sauce. Yeah.
Just real quick, the secret sauce is really an administrative thing, meaning that many, many years ago, this was the foundation for like some sort of commercial endeavor, and they realized this is actually not a commercial endeavor for us. And then engineers being engineers, oh, we'll open source it, we'll open source it, we'll open source it. So very soon it's going to be open source. It's merely an administrative function.
Yeah.
Perhaps laziness on the engineering side.
Yeah. Okay. Well, maybe I can like sneak you the source code for it. Holler at me. We'll see. But yeah, this is essentially the algorithm here. I'll let you read more in detail whenever you get the link. Cool. So what else did I want to show you guys? So we did that reverse image search, we've done text search, we've done comparing different model representations, we looked at representativeness, uniqueness. Here's another one that I think might be interesting for folks that are working with kind of text-based RAG. In this case, here's what I did. I have a data set here. This is a data set of CVPR papers, and I used one of the plugins that we have in FiftyOne. So FiftyOne, open source, everything is kind of community-driven. One of the awesome things that we have is community-driven plugins. So you can extend the functionality of FiftyOne however you want. Whether you share that with the community, keep it for yourself, that's entirely up to you. But this plugin that we have here is actually an OCR engine plugin, and then a semantic document search plugin on top of that. So what I did was, we'll see it here in a second. So what this data set is, it's just the first page of a number of papers that were accepted to CVPR. We did optical character recognition on top of that. Then we extracted that text, took that text, converted it to some embedding representation, and stuffed all of that into a quadrant vector database. And now what we could do is actually search over this image data set. So now, I mean, you could think for yourself if you have if you got data sets that contain, for example, images with text in them somehow, this unlocks a lot of really cool things that you could do, right? So let's go ahead and just open this up. Backtick, open the operators panel here. It will say semantic search. And maybe the query, I don't know, 3D, just a bunch of buzzwords. 3D Gaussian splatting, meshes, and diffusion. Let's just lower that threshold for matching just for illustrative purposes. And now what we're going to get is the PDF like images, that front page, but then also the text block which kind of matches that. And so you can see here, we're getting matches here. Look, 3D Gaussian splatting, that's great. And then also this paragraph has some type of similarity to that query as well. Likewise here, right? And again, this is all just based on, this is semantic search, so it's not keyword-based search. We also have a keyword-based search plugin that you can just do strict keyword. I mean, there's scenarios where keyword matching is a lot better than doing semantic searching. You could do both in FiftyOne. Cool. Now this is the last one. This is going to be like super abstract and weird and like, you know, kind of out there. And even the images we're going to look at might induce an acid trip. But we're going to do something called concept space traversal and then concept interpolation. And so this is also a plugin that was developed to kind of extend the functionality of FiftyOne. Essentially what we're going to do is we're going to have an embedding space, and in this case, again, we are using the clip embedding model. I use clip primarily because I'm doing everything locally, and clip is just super fast. But once I put that GPU that NVIDIA gave me to work, I'll use heftier models. And if NVIDIA wants to keep sending me GPUs, JRush, let me know. I'll give you my address. But to do concept space traversal, we'll have some embedding space, some similarity measure. In this case, we'll use cosine. And then what we're going to do is actually that embedding space that was generated, we can actually walk it. We can move across that embedding space. And we do it by essentially vector arithmetic. So we could take an image, and with that image, convert it to some representation using clip. And then in concept interpolation, we could have two concepts and weight them differently, get the embedding for that concept, and in this case for, I don't have the code here, concept interpolation does this. So we're given a left prompt and a right prompt, and we're interpolating it just like a linear interpolation between two prompts. And we just add that essentially to the image embedding. And so then we could see kind of just walking across our image data set with text. It's quite interesting. We'll see in just a second. And then, that's that one concept interpolation, but you can also do something more complex. Let me just open it up and show you guys. A lot of details here. If you guys want that, you'll get emailed a link to this GitHub repository, so you'll be able to read that on your own time. So let's go ahead and launch the app. So this is like a trippy data set. It's called color swap. And something like, what? What was that? Let me just clear that. Clear that. I had multiple, oh my God, dude, demo gods, man. Here, hold on. Jupyter notebooks suck. Cool. So let's go ahead and play around with this. So first, let's go ahead and do this kind of interpolation. So I'll move this to the bottom here. And we can select some image. I don't know, which one looks good to you guys? Let's just do this, and then we can select between here. And so we have two different concepts that we can kind of interpolate with, and we can weight towards one, towards the other. What's going to happen is we'll compute an embedding for this particular prompt, weight it however we want. So we can weight it more towards Wicked, we can weight it more towards the Glenda the Good Witch, and then just do vector arithmetic, essentially taking this and then just adding it to the image prompt here. So in this case, actually, let's take that one. Let's go ahead and execute that and see what we end up with. And so remember, the limitation here is like what's in our data set, right? So if you are, trying to traverse to a concept that isn't represented in your data set, you're not going to get good results. But you can see here, more or less, we get some, I said Glenda, the Good Witch, weighted it really heavy towards that. This was the initial image that I had selected. And, we kind of walk that space in a really, really cool, interesting way, right? So kind of just bring it to life, what it is that we're doing. That's okay. I did something weird. I don't know why there's not all the embeddings here. User error, whatever. But you've seen an embedding space, so you kind of know what they look like, right? I've showed you some. And so we've kind of traversed this embedding space, by taking a starting image right here and weighting a concept and moving to, for example, this image or that image. That's weird. Yeah. So this is our image embedding space, and we're just kind of traversing it and walking across that. And the next thing we could look at is concept traversal. And this is essentially what we're doing before, but with a couple more kind of settings to it. You can weight it differently. You can add multiple concepts and things like that. So let's go ahead and just see that in action. So we could start with this image, and maybe concept one we could say is cute and fluffy. And we can weight that by whatever weight. Concept two, maybe we want to say not only cute and fluffy, but we want to say kind of like a nice pet. And maybe we can weight that a lot. We'll start with this one. We'll set that initial image. And so we're going to, okay, see if I take the representation of this image, of this really wicked, scary-looking alien, and to this scary-looking alien, I'm going to add 2 vectors that are weighted differently. One vector is going to be the embedding for cute and fluffy. Another one will be for a nice pet. And we're going to traverse this embedding space to see where we end up. And then we can also, this is like the guidance scale. So that's that guidance scale hyperparameter. So we'll traverse that and see where we end up. And you can see we get some, this is like actually pretty cool. So we get like some, that's kind of cute-ish. We get fluffiness, nice pets, and things like that. So we walked and moved across our embedding space. That's it. That's all I have for you guys. Hopefully, you guys enjoy that. Like, I can get lost literally for hours and hours and hours looking at embeddings. I think they're the coolest thing in the world. And hopefully, now you guys think they are as well. Thank you.